Hello everyone, welcome back to our channel. Today is the day 2 of our Verilog series and the topic of the day is ASIC Design Flow. So without further ado, let's start today's talk. First of all, what is an ASIC? If we go by its full form, ASIC is an application specific integrated circuit. As the name suggests, ASIC is a type of integrated circuit which is made to perform a specific task. So what benefits does ASIC provide? ASIC has been optimized for speed, power, and area in the targeted applications such as networking, telecom, and multimedia. ASICs offer superior performance and power efficiency for the specific task that they are designed for. Any processor which you are using in your mobile phone or laptop is an example of an ASIC. So, what is ASIC design flow? ASIC design flow is an overall process which contains various steps for the fabrication of an ASIC chip from start to the end. This image shows what are all the steps involved in a ASIC design flow. We will be starting from design specification all the way till implementation. Now let's discuss each of the topic one by one. The first step in any ASIC design process is the design specification. That is, this this is a document, specific document, which defines the functionality, performance goals, and the constraints of the ASIC. In simple terms, this will tell us what are all the functionality that a chip will perform. This can be ranging from a simple chip which is just used to add two numbers or even complex chip such as a processor. These are written by system architects based on the application need. That is, a chip in your smartphone will have different set of requirements than a chip which is used in a washing machine. Both of their applications are different, hence they will be having different specification. The next step is behavioral description. In this, we describe what are all the functionalities that a chip should have at a higher level. These models can be made in C, C++, or System C. The third step, which is RTL description, there is register transfer level logic description. Here, the requirement of Verilog starts. We describe the specification that were mentioned in the spec. To achieve those specifications, a design is made at the register transfer level using any hardware description language such as Verilog or VHDL. Here, the focus is on clock-based behavior and data flow. The next step after the design has been made is functional verification. This ensures that the design which has been designed earlier in Verilog matches the specification which were decided in the first. The functional verification step is performed by verification engineer. They make sure whatever design the design engineer has made should perfectly replicate the specification that were mentioned. Once the functional verification and testing has been completed, we move to the fifth step, that is logic synthesis or timing verification. In this step, the RTL is converted into a gate level netlist using synthesis tools. Here, the concept of setup and hold time is also that the design should meet all the setup and timing constraints. So, to avoid any setup or hold time violation. The next step after this is the gate level netlist. A netlist representing the whole design in terms of logic gates and connection is developed. This netlist will be used for the further steps of physical design process. The seventh step is logical verification and testing. We revalidate all the functionality at gate level. Earlier, the functional verification was performed at the RTL level. Now, the verification is being performed at the gate level to make sure that no bugs are left. Includes formal verification and gate level simulation. Once we are done with logical verification and testing, the next step involves the floor planning and automatic place and route. Here, the role of physical design engineer comes in. They take a look at how will the chip which has been designed using Verilog be placed physically. And once the floor planning and automatic place routing is complete, the overall physical layout is designed to make sure the design is optimized for both area and power. After the layout has been designed, the layout verification takes place. Checks for DRC, design rule check, layout with schematic and antenna rules are made sure that they are all being followed. Ensures that the layout is manufacturable and matches logic. And the last step, once we are done with all the verification, whether it's at functional level, gate level, or layout verification, then the final GDS file is sent for fabrication. And that results in an actual silicon ASIC chip. Now, you all must be wondering, why are there so many layers of verification for this ASIC chip? In this design also, you can see there are some back arrows. It has been traced to the RTL description or HDL level. This is because whenever a chip goes for implementation or fabrication, which is the last step, the chip needs to be bug free. You may ask why? Because once the chip has been fabricated, and after that, if any bugs are found, then it's not possible to fix those bugs. And if a chip with bugs is sent to the market and any consumer finds that bug, it's very detrimental to the reputation of the company as well as it will lead to economical losses. So, there all the possible measures are taken to make sure that chip is as bug free as possible. And this back arrows indicate that at any level of verification, if we found out that there are any kind of bug, then the whole process iterate back. If we find a bug in functional verification testing, then that is communicated to the RTL design team so they can make the necessary changes. If the bug is found at a logical verification or testing level, then also the design has been sent back and again all the steps take place. Ultimately, this process will take place that there are no bugs found, and once the design is fully verified, only then it's passed for fabrication. So this was an overall overview of the ASIC design flow process. If you guys have any doubt, please feel free to ask them in comments. From the next video, we will be starting Verilog.